So now we're going to take a look at example 2, which is very similar, but we change it just a little bit. So it's the same thing. We have codes we can create of 3 numbers and 2 letters, but repetition is not allowed. Okay, so I'm going to set it up in the same way I did this last one, with number, 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 letter, letter. So we have 5 spaces, 5 characters in this code. Now, to start with, there's 10 possible different numbers from 0 to 9. But now we're not allowing repetition. So once you pick a number, you can't use that number again. So for this next spot, this next number, there's only 9 choices, right? Because we picked a number for this first spot. That's gone. We can't pick that number again. So now there's only 9 remaining choices. Same idea for the next. If this next one is also a number, well, we already picked 2 numbers, so we can't pick those again. There's only 8 choices left. All right, so basically we're just kind of decreasing by 1, because as we use a number, we can't reuse that number. So we're left with 1 less options. Same for this third number. Okay, and then the letters. There's 2 letters. So once again, the first letter, we have lots of choices. There's 26 letters in the alphabet. Now, if we pick one of those letters and we can't reuse it, how many letters do we have to pick from for the second letter? 25. And now we're going to multiply all of this together. So I'm popping it into my calculator real quick. I get 468,000, which is less than example 1, which makes sense because, again, we're not allowing any repetitions. No letter or number can be repeated. And same idea, with the ordering. It doesn't matter if you do letters first, you do numbers last, you mix it all up, you're going to get the same number in the end because we're multiplying all those numbers together. Okay, let's look at another example. Number 3. If 7 children are lining up for recess, how many different ways can they line up? Okay, so we got 7 kids. So I'm going to make a space for 7 different objects. 1, 2, 3, 4, 5, 6, 7. Okay, so we have 7 children lining up. So the first spot, there's 7 different possibilities, right? Any of those kids could be in that very first position. Okay, now this question doesn't mention repetition or not, but think about the problem in context. If one of those kids is in the very first spot, can that same kid also be in the second spot or the third spot? No, that is not possible in our universe in any way. We could not be in 2 places at once. So naturally, this is a problem with no repetition or without replacement. So sometimes it's not always explicitly stated. It's just, context of the problem. We can't repeat humans. So if one of these 7 children takes this first spot, how many kids are left to take that second spot? Well, 6. How many are going to be left for that third spot? 5. How many are going to be left for the fourth spot? 4. See a pattern here? Keep going. And then, as everyone starts lining up, there's only going to be 1 person left to take that last spot. And so to figure out the total number of different ways, we multiply these numbers together. And this one I actually did before I did this video. So it is 5,040. So there's 5,040 different ways these kids can line up. That's a lot. All right, let's do one more. The college's soccer team will play 11 games next fall. Each game can result in one of 3 outcomes: a win, a loss, or a tie. Find the total possible number of outcomes for the season record. All right, so there's 11 here, and I'm not going to draw all of these because something cool is going to happen on this problem. So let's just start with the first 3 spots, and well, let's do 4 spots, and then we'll see if a pattern emerges. So for this is the first game, right? Here, instead of a arrow, this is game number 1, and then this will be game number 2, game number 3, game number 4, okay? So how many different outcomes can we have for game number 1? Well, there was 3 possible outcomes: a win, a loss, or a tie. So there's actually 3 outcomes here. Now the second game, how many outcomes do we have for that second game? So again, it's all context of the problem. Technically, there repetitions allowed. You can win 2 games in a row. You can lose 2 games in a row. I mean, you could really lose all 11 games in a row. So this is a problem where we can repeat. So for that second game, there's still 3 options. For the third game, there's still 3 options. For the fourth game, 3 options. So see the pattern? I didn't want to draw out all 11 lines. So all the way to the 11th game, no matter what, every single game has 3 different options. So basically what we have to do is multiply 3 by itself 11 times. But, I mean, by all means, type that in your calculator. 3 times 3 times 3 times 3, so on and so forth. However, we can rewrite that as an exponent. An exponent is basically repeated multiplication. So this is the same thing as 3 to the 11th power. There was 11 games, and there was 3 outcomes for each game. So it's 3 to the 11th, which is, it's the same thing as 3 times 3 times 3, 11 different times. But it might be easier to type 3 to the 11th into a calculator. So once you calculate that, we get 177,147. So those are the total number of ways that season can go, which that's a lot, I think. Okay, so that is the fundamental counting principle. Basically, you just figure out the number of ways for each individual, experiment or whatever the context of the problem is, and we multiply all those numbers. You just have to, read the problem and figure out, can we repeat things? Can we not? So on and so forth. Okay. So we definitely have a lot more to talk about this week. And all of that will be presented in future videos. See you then.